All right, so we're going to do our first example of volume of solids. This is a cross-section problem, which will be obvious as I start reading the problem to you. So the region bounded by y equals x squared plus 1, x equals 2, and the coordinate axes is the base of a solid whose cross-sections perpendicular to the x-axis are squares. Find the volume of the solid. So again, when you see the word cross-sections and they tell you perpendicular to the x-axis are squares, that's a hint that what you're looking at is a cross-section problem. So we're going to draw this diagram. So let's start by drawing what this graph would look like. And it doesn't have to be a beautiful graph, but x squared plus 1. So 1, 2, 3, 4, 5, right? So 0 squared plus 1 is 0, 1 squared plus 1 is 2, and 2 squared plus 1 is 5. So essentially, I'm looking at this parabola, right? I'm looking at this parabola from 0, which is the y-axis, to 2, because they said x equals 2, and then I'm bound by the axes. So the area that I'm looking at is this shaded region right here, okay? Now, standing up on each one of these, one easy way to think of these cross-section problems is think about it like this is a dish rack. So I have square dishes, and the square dishes are sitting perpendicular to the x-axis. So at some random spot, I'm going to draw a square coming out of my board. Right now, it's hard to draw 3D on these things, but I'm looking at a square that's coming physically off the board, right? So I'm going to borrow my eraser for a sec. If I stood my eraser up off the board, right, coming directly off the board, so it's a rectangle, but pretend for a sec it's a square. If I stand it up off the board, that's what we're looking at. So the area of this one square, right, in terms of x, is going to be whatever this base length is, quantity squared, because it's square. So essentially, it's base times base. If I can find a way to write this base, now on the picture where I'm drawing, it kind of looks like it's a little bit more than 1. But remember that I need this base in terms of x, because what's happening is these squares aren't all the same size. The square at this end is a very tiny little dish, right? And the square at this end is a very big dish, right? But they're different size dishes, and those dish sizes will vary as x. In this case, as x gets larger, the dishes also get larger. That's not always true. So the way I'm going to find this base length right here, right? So if you look at this square, I've got this base length, right? So this is my square. This base, anytime I want a vertical measurement, I'm going to do top value minus bottom value. So in this case, my base is top value, which is the curve x squared plus 1, that's the top value, minus the bottom value, which happens to just be the x-axis, so that's a y value of 0. So in this case, that base length is x squared plus 1, which is why it was a very small base when x was 0 and a very big base when x was 2. So I'm going to write this as x squared plus 1 times x squared plus 1, right? Or you could write it as the whole quantity squared. The trick is that the volume is not one of these dishes, but the sum of all these dishes. So if this is your area, the way you find the volume is by integrating to add all the dishes. So you're going to integrate your area with respect to x, so a of x dx, from the start of the dishes, which happened to start at 0 in this problem, to the last dish, which ended when x was 2. So from 0 to 2. So that means that I'm going to integrate. I'm going to have to FOIL this guy out since I'm doing it by hand. If I had on a calculator, I could just go ahead and type it in. But I'm going to end up getting x to the 4th plus 2x squared plus 1 with respect to x from 0 to 2. This is another problem where I'm going to get some super fun fractions. But when I integrate my volume, I'm going to get x to the 5th over 5 plus 2/3 x cubed plus an x, right? And I'm going to do from 0 to 2. So at least the 0 is going to be friendly, because when I plug zeros into the polynomial, they'll all come out to be zeros. So I'm going to end up with a 32/5 plus, this would be an 8 times 2, so 16/3 plus a 2. So my common denominator, minus a bunch of 0, right? If you plug in 0 and 0 and 0, they all zero out. Don't forget to plug in the bottom bound. It's just in this case, it wouldn't have mattered. My common denominator is going to be 15ths. So I'm going to have to times the 32 by 3 to get 96. So that's 96 15ths, right? I'm going to have to times the 16 by 5 to get an 80, right? 80 15ths. And I'm going to have to times the 2 by the full 15 for the common denominator to get 30 15ths. So I think that when all is said and done, I get that my volume is, let's see, that would be 110, right? So that's 90, so 206 over 15. 206 is not divisible by 3 because its digits don't sum to 3, or a multiple of 3. They sum to 8. And it's not divisible by 5 because it doesn't end in a 0 or a 5. So that's my final answer. If you wanted to check this in a calculator, it's not a bad idea, right? The way I would check this in my calculator is I would put y1 in my calculator as my x squared plus 1. Sorry, computer drifted off. And then I would go ahead and put function integrate, which is math 9, right? Function integrate of my y1 quantity squared, comma, with respect to x from 0 to 2. When I get an answer, I would then math frac it. And hopefully it math fracs to 206 over 15.